Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. So in this subject, in the previous session, I have discussed about shear stresses and bending stresses. So how to calculate torsional shear stress whenever circular shafts are subjected to load. So now in this today's topic is distribution of shear stress in a circular shaft subjected to torsion. So how to draw the distribution of shear stress whenever the circular shaft is subjected to torsion, we will see in this today's session. So the outcome of this topic is the students should be able to analyze the theory of pure torsion, bending to draw shear stress distribution diagrams in circular shafts, and then bending moment distribution diagrams in various cross sections of beams for different loading types. So in this, after completion of this module, the topic, the student should be able to analyze the theory of pure torsion, bending to draw the shear stress distribution diagrams in circular shafts, and the bend moment diagrams. They will be familiar after completion of this topic. So this is the outcome of this today's topic. So in this, the distribution of shear stress in circular shaft subjected to torsion. The topic, the distribution of shear stress. So whenever the circular shafts are subjected to torsional loads, so how the shear stress is distributed throughout the circular shaft. So you know the simple torsion equation already we have derived in a previous session. T by J is equal to tau by R is equal to G theta by L. Or you can write the shear torsional shear stress tau is equal to G theta into R by L. So in this, T is torsion and J is the polar moment of inertia. T is the torsion and J is the polar moment of inertia. And tau is the shear stress and R is that radius of circular shaft, or that is actually you already we have derived in previous session. So in that session already we have observed. So what is R and what is tau and G, theta also we have seen. So in this, the theta is the modulus of rigidity, that is angle of twist. Sorry, G is the modulus of rigidity. This theta is the twisting moment or angle of twist. Angle of twist. And L is the length of the circular shaft. So whenever, suppose the circular shaft is subjected to torsional load, so this is center and radius or it is angle theta. Yeah. So by using this diagram, already we have derived the simple torsion equation T by J is equal to tau by R is equal to G theta by L, the polar moment of inertia. So for circular rod, pi d to the power of 4 by 32. And G value modulus of rigidity, the angle, testing angle, and L also, you know. So this states that the shearing stress varies directly as the distance r from the axis of the shaft. The following is the stress distribution in plane of cross section and also the complementary shearing stresses in an axial plane. It states that the shearing stress varies directly as the distance or from the axis of the shaft, and the following is the stress distribution in a plane of cross section. So we will see in this diagram. So in this diagram shown the stress distribution in the plane of cross section. So here given one is solid shaft, another one is hollow shaft. You know the solid shaft is having only one diameter, and this one is inner diameter and outer diameter, having this hollow shaft, outer and inner. Capital T. So the plane of cross section and also complementary shearing stress in axial plane. So you see the cross section, after cross section you can see the shear stress distribution in a solid shaft and similarly in a hollow shaft. So hence the maximum shear stress occurs on the outer surface of the shaft. So that is the outer surface of the shaft, the maximum shear stress will be occurred. So that is nothing but that R is equal to capital R. So the value of maximum shear stress in the solid circular shaft can be determined as, how do you calculate? By using shear stress equation. Tau by R is equal to T by J. The shear maximum when R is equal to D by 2. So that is, you can calculate the shear stress is equal to T into R by J. The shear maximum where R is equal to D by 2. So here the capital R where R is equal to capital R and T by J is equal to, already you know, 5 d to the power of 4 by 32 for the circular rod. But the R is equal to D by 2 here. So substitute where D is the diameter of the solid shaft. So we will get shear maximum. We will get shear maximum, that is 16. So do you calculate this one? T by 5 d to the power of 4 by 32 into D by 2. So here 16 t by dt get cancelled here, 5 d. 16 d by 5 dt. So this is the final shear stress equation. The maximum shear stress equation occurs at on the outer surface of the shaft. So from the above equation, the following conclusion can be drawn. The shear maximum is directly proportional to T torque, and also the shear stress maximum directly proportional to 1 by dq. So that is here shown here in this equation. One is shear maximum directly proportional to T and directly proportional to 1 by dq. So how do you calculate the power transmitted by shaft? So in practical application, the diameter of the shaft must sometimes be calculated from the power which it is required to transmit. So given the power required to be transmitted, the speed in and torque, the formula connecting, what is the formula? These equal quantities can be derived. And the formula is equal to T into omega. So the power required to be transmitted, one is N is the speed and T is the torque. Now you can write omega is equal to 2 pi n by 60. So substitute in this T 2 pi n by 60. So again rewrite the above equation, 2 pi n T by 60 to 10 cube kilowatts. So the torsional stiffness K is defined as the torque for a radian twist. So here the torsional stiffness K is equal to T by theta. So that is Gj by L. So what is G? Modulus of rigidity. J is the polar moment of inertia and L is the length of the circular shaft. So this one T by G data by T by J is equal to T by J is equal to G data by L. It's already we have derived in the previous session. So from this equation, so write this equation formula K is equal to Gj by L. So this is called as the torsional stiffness, that is represented with K. So for a ductile material, the plastic flow begins first in the outer surface. See any ductile material. So example, mild steel. For a material which is weaker in shear longitudinally than transversally, for instance, a wooden shaft, with the fibers parallel to axis of the first crack will be produced by the shearing stress acting in the axial section, and they will appear on the surface of the shaft in the longitudinal direction. So when a material is which is weaker in shear longitudinally weaker than the transverse, for instance a wooden shaft, so with the fibers parallel to axis of the first cracks will be produced. So in this case of a material which is weaker in tension than in shear, for instance a circular shaft of cast iron or a cylindrical piece of chalk, a crack along a helix inclined at 45 degrees to the axis of the shaft. Suppose if you take a shaft, this is shaft axis, the crack along a helix, so angle that is theta 45 degrees. So the weaker in tension than in shear. So the weaker the shaft elongates. Now we will see the torsion of hollow shaft. So up to now I have discussed about torsion of solid shaft. So now from the torsion of solid shafts of circular X section, it is seen that only the material at the outer surface of the shaft can be stressed to the limit assigned as an allowable working stress. So all of the material within the shaft will work at a lower stress and is not being used to full capacity. So all of the material within the shaft will work at a lower stress. So thus, in these cases where the weight reduction is important, it is advantage to use hollow shaft. So the weight reduction we will see. So how to calculate the weight reduction? So it is advantage to use the hollow shaft. So in discussing the torsion of hollow shaft, the same assumptions will be made as in the case of solid shaft. So whatever you have taken in solid shaft derivation of torsion equation, same assumptions here we should follow. The general torsion equation as we have applied in the case of torsion of solid shaft will hold. So there's the same assumptions. What are the assumptions? So assume the material is homogeneous, having homogeneous property, and the cross section is uniform cross section. So the material having elasticity property, and the assumption you should follow the Hooke's law. So all these things are assumptions. So here also you apply same assumptions. The cross section of the solid shaft is uniform. Similarly, here also the torsion hollow shaft cross section also uniform. So suppose the hollow shaft you take here. So this is outer surface. The outer surface is capital D, inner surface is small d. D and capital D. So remaining all are same as solid shaft. So take the torsion equation. T by J is equal to tau by R is equal to G theta by L. But in this case, for the hollow shaft, the J is equal to pi into D naught to the power of 4 minus Di to the power of 4 by 32. So what is D naught? Outside diameter. What is Di? Inside diameter. Now you can take Di is equal to D naught by 2, or otherwise D naught is equal to D 2 times of the inner diameter. So in this hollow shaft, J for solid shaft already you know pi d to the power of 4 by 32. But in this case, solid shaft having only one diameter, but here having inner and outer diameter. So that's why calculate d naught is outer external diameter minus inner diameter to the power of 4 by 32. So the maximum solid shaft shear stress is 16T by pi d naught to the power of cube. As already we have seen in starting slides. So in this, for hollow shaft, substitute the T value here and J. For hollow shaft, T is equal to shear T into D naught 2 by R. T R. Shear max is equal to T R by J. So why? Because so already we have derived the equation tau by J, T by J is equal to tau by R. T by J, that is equal to G theta by L. So from this equation, shear max is equal to T R by J. So here R is equal to D naught 2 by 2. So external diameter, half of the external diameter, divided by J pi by 32 D naught to the power 4 minus Di to the power 4. So now simplify this equation. After simplification, you will get (16T by pi d naught cube minus 1 minus so you will get 1.006 (16T by pi d naught cube). So hence, by examining the equation 1 and 2, so it may be seen that the shear maximum in the case of hollow shaft is 6.6% larger than the case of solid shaft. See, solid shaft is 16T, shear maximum is equal to 16T by pi d naught cube. But in hollow shaft, this is solid shaft. For a hollow shaft, 1.066 to 16T by 10. So nothing but in the percentage 6.66% larger than the in a solid shaft having the same outside diameter. So next one is reduction in weight. So the considering a solid and a hollow shafts of the same length L and carrying and the density is R with DI is D naught by 2. So here the weight of hollow shaft is, now calculate area into L into density. So here density rho. So pi d naught square by 4 minus 5 d naught square by 16. After simplification, we will get 0.75 pi d naught square by 4 into L into rho. So the weight of solid shaft is 5 d naught square by 4 into L into rho. So reduction weight. So the reduction weight is 1 minus the solid shaft weight. The solid shaft weight is area multiplied with length into density. So density is equal to mass per volume. So volume A into L. So that mass is equal to volume multiplied with density. So the volume is A into L. So the weight of solid shaft is pi d naught square by 4 into L into rho. So the reduction weight is, now subtract the weight of the solid shaft into pi d naught 4 by L into rho. You will get 0.25 into pi d naught square by 4 into L into rho. So hence the reduction weight would be just 25%. Clear? So now example I will show you this distribution of shear stress in circular shafts subjected to torsion. So a stepped solid circular shaft is built in at its ends and subjected to an externally applied torque. So the T naught at the shoulder as shown in the figure T naught. Determine the angle of rotation theta naught, the angle of rotation theta naught of the shoulder section where T naught is applied. Here, so what is the angle? Theta or gamma? So D1 diameter, this is a stepped solid circular shaft. So here D2 is having another diameter and D1, and at A, this one subjected to torsion, and distance is also given. So now this is statically indeterminate system because the shaft is built in at both ends. All that we can find from the statics is that the sum of two react to torque. The TA and TB at the built in ends of the shaft must be equal to the applied torque, that is T naught. So T naught is equal to TA plus TB is equal to T naught. So where the TA and TB are the relative torque at the built-in ends A and B, where T naught is the applied torque. See, from consideration of the consistent deformation, we see that the angle of twist in each portion of the shaft must be same. So the angle of twist, that is theta A is equal to theta B is equal to theta naught. So using the relation for angle of twist, T by J is equal to G theta by L. So already we have derived this equation. So now find out theta A, the angle of twist, TA, torsion at A into distance, TA by JAG. Similarly, theta B is equal to TBA by JBG. So compare these two, substitute in this equation. You will get TA by TB is equal to JA by JB into B by A. So assuming the modulus of rigidity be the same for the two portions. So why? Because that the material is same. So the define the ratio of T and TB by solving 1 and 2 by 1 and 2 equation. This two equation already one equation TA plus TB is equal to T naught. So TA plus TB is equal to T. So by after solving these two equations, you will get theta naught, TA and TB. TA is equal to T naught by 1 plus JBA by JAB. TB is equal to T naught by 1 plus JAB by JBA. So what is T naught? The torsion at O point, the shoulder portion. Similarly, the polar moment of inertia at B and the polar moment of inertia is at A. So the polar moment of inertia here shown diagram is solid shaft. So here J naught or JA here given JA and JB. So you can calculate JA is equal to 5 D1 to the 4 by 32. Similarly JB 4 by 32 D2. So substitute, you will get. So using either these values in 2, we have the angle of rotation theta naught at the junction. So at the junction, theta naught we will get. So like this, how to calculate the angle of twist. So the angle of twist for a stepped solid circular shaft. So whenever having two diameters. So these are the references I have taken for this PPT. Ramamurthy, S. Ramamurthy Mother and the strength of material is the textbook title, and R.K. Bansal, textbook of strength of materials title, and R.S. Kurmi and Gupta. Title of the book is Strength of Material, and I have taken the NPTEL Strength of Materials lecture notes for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.